this video is about exploratory data analysis, and we're going to be using the crop dataset from Kaggle. So the first thing we do is to import our libraries, and one of the things I need to say here is we're going to be using Kaggle Hub, and Kaggle Hub is what helps us to get the dataset from Kaggle easily, and we're going to see how that works now. And this is it from Kaggle Hub, and we are using this dataset, crop prediction dataset. We can see the same dataset here, and in this code, we have the path to the file being generated directly from Kaggle Hub dataset.download. So when I load it, it may take just a short time, and now we see it. So we have the path to the dataset now stored, and we can list whatever is in the directory using os.list directory and pass the path in it. So we can see the files yield, temp, rainfall, pesticide, yield df, and we can see the same thing here. So we're able to pull the dataset, but what we need mainly is the yield df.csv. And we just say df is equal to pd.csv using pandas, and say pass the path into this f string, then we say slash yield df.csv. So if you want to understand pandas better, I have videos on this channel on introduction to pandas, and you will see the main information to everything. So I'll just move on with the exploratory data analysis here. So I'll load the data, and I can check. I'll say df.head here instead. Df.head, I'm using to see the top 5 rows in the data set. And we can see unnamed area, then we have all the rows, the top 5. But if I want to see the bottom 5, I can say .tail, and that will show me the bottom 5. So head, top 5, and tail, bottom 5. So the next thing as we explore this data is to see the shape of the data. So here the length of my data is 28,242, and I have 8 columns. So that is what this output is showing. I will move to the third path, which is to explore the data, and we go one by one by saying, okay, in 3.1, data types and structure, and I open that. And the first thing here is df.info. And for df.info, we see it's showing us the metadata basically of the data set. So we have the area, and we have 28,242, and it is the same for all the columns. We have no missing value, and we have this as integer. We have area and item as object, and they are object because they are a string column and string, or what you call a text. So you can see area and item. You have Zimbabwe, rice paddy, and other things are numeric basically, and numeric can be integer, and it can also be float. Float if it has points, if it's decimal, and integer if it is just integer value, a real number, or what you say, a single value or a non-decimal number. So basically, so that is it. Now we say df.describe. We say df.describe, and I'll first remove this .t. So when I do df.describe normally, it's going to show me this way by column. Then I'm going to say count mean standard deviation of each. But when I say .t, I'm transposing whatever I have in this output so that I can have the column in the right, and so I can have the column name as the index of this table. And we're going to see that. So we can see that this as the index. You can see year, yield, average temperature, then mean, standard deviation, minimum, 25%, 50%, and maximum. So we move now to the summary statistics. And the summary statistics, just like what we did here, we have the summary statistics to describe the data, but this is only describing the numeric data. So for this, we want to describe specifically the object, and that is the string value, that is area and item. That's what we want to describe. So when I run this, you can see what I can get in the summary statistics about the count, the unique values we have, 101, the item, we have 10 unique values. Then potato is the top crop, that is the top item. Then India is the top area in the data set, that is top country with the highest number of rows or highest number of records. Then the frequency is 4048, 4246. That is the number of its occurrence. Now, NUnique. What NUnique does is NUnique, normally this df.describe is showing me the unique value, but NUnique will show me the unique values that we have in all the columns, not just the string column or the object columns only. So when I run NUnique, you can see for each of the column, we have the unique value counts that we have in the columns. So here unnamed, we're going to be dropping it because we don't really need it. It's just the index that was not dropped while they were saving the data set. So that is what will move us into data cleaning. And for data cleaning, we start from here to remove the unnamed. And to do that, we use df.drop, and we'll pass the axis. So axis equals 1 is saying drop unnamed as a column, or name is a column, so it's on axis 1, which is column. If this happens to be 0, that is the row axis, but it's a column, so we say axis equals 1. Then in place equals true means just save it back after dropping directly. So when I run this, you can see we don't have the unnamed anymore. So now I want to see the value count of the areas to just see the areas and the number of times that each area occur. We know that India is the highest. Here we want to see how many records basically per area. So when I look at this, see India 4048, and we have it up to we have Montenegro having just 24 occurrences or 24 records. So with that, for the future project that we're going to be doing after this, which is the building machine learning model for this to predict the crop yield based on these variables, this may skew our data in a way, may not make things balanced. So just to do a bit of cleanup, we're going to remove countries or areas where we have less than 100 records. And that's what we are doing here. So the first thing we do is we pass this value count into country count. So we have this variable, and then we're going to be creating a list called countries to drop. And how we do that is to take this country count variable that we generated, and we just say country count less than 100. Then we pass the index to list, and we're able to have the country. And then we filter out those countries that we want to drop, and this is helping us filter it out. So what the tilde sign is doing is it is helping us to remove every row that follows this condition. That is every row where the area is in countries to drop. So it will just drop them. Then we print the remaining by saying df.area.n unique. So we just want to print the remaining countries and then see the remaining rows. So here now we have 71 countries left and 26,000 rows left. So the next thing here now is the categorical columns. So normally in a machine learning project, we will have our categorical columns, but here we just want to pass the categorical columns into a specific variable, into a list. Then we have that, you can see area and item. So here also can be a categorical column, and sometimes some people may leave it as numeric. But we'll see that when we do build the machine learning project in the following video after this. So we move forward into missing value analysis. And for missing value analysis, this is what we do. So for the missing value, we use df.isNull.sum. Although we've seen before that in this data set, we don't really have missing value, but it is good to still show it. So here we say print df.isNull.sum. So this is going to show us the missing value that we have in each of the column, that is in each variable. Then here we say total missing value. We don't want to count the total missing value in the entire data set. So instead of stopping at its sum, then we add another sum method to it. And what the sum method is doing is to ensure that we have the total, not per variable, but in the entire data set. And here we're just calculating the percentage of the missing value compared to the total length of the data set. Then we have that. So you can see 0 per column, and we have 0% in terms of the percentage of the missing value. So now we move to analyzing the missing values. So just to have a plot of the missing value, because sometimes you may actually have multiple columns and you just want to see which column has the highest missing value and just visualize it. That is what we are using the Seaborn and building a heat map for the missing value. And this is how the code follows. So using the df.isNull, capture the missing values, the C bar, that is, they make sure the bar follow a specific color gradient, and we pass the color gradient, that the C map follow a green color gradient, and we just run that. And we can see, because there's no missing value, everything is the same color. But even we have missing values, we see a gradient like this that follows for each of the column in the data set. So we can now move to the next thing. And for the next thing, we are doing our univariate analysis. And for the univariate analysis, that's when we do the distributions, we do the box plot, we do box plot by crop type, we do the skewness analysis, and all of the things that is possible that we're not even doing here. There's a lot more that one can do. So the first thing is to plot the distribution of the data. And here we are using this hist method and df.hist, but before that, we select the data type. So we want to do it for the numeric. That's what we say include number, not object, not the string values. So we just plot this in 30 bins. So we just wait for that to run. So we can see the year, this is the distribution. But what I want you to see is look at the yield. You can see that it is skewed, okay? But we're still going to do the skewness after this for us to have a number for the skewness and say, oh, the skewness is moderately skewed, extremely skewed, or not. So you can see the year is skewed. The pesticide tons, that is pesticide per ton applied, we can see it's also skewed. Then we can see the average temperature is skewed a bit to the left. So you can see this. Well, this average rainfall is a bit scattered, not as skewed as other ones. So that is one of the things we can see with the distribution of the numeric variable. So we'll move to the next thing and detecting the outlier. So outlier detection is very important. That is, we want to see what are those data points for, let's say, the whole data set, or for specific crop type, or let's say in the specific column that we want to talk about, what are those data points that are far away from the normal range of the data set. And to do outlier detection, we use boxplot. So here, what this for loop is just doing is this for loop is looping through each of the column in the numeric columns that we have. So we can see we don't want to do it for the year column, so that's why we drop the year. So loop through the numeric columns that we've selected, and of course this is a plot panel setup, and plot have a box plot for each of the column, and that is just what we are doing. That's why you have the whole data frame as the data, then you have y as the column. We don't have a specific x-axis in this case. So when I run this, you can see. So just like what we've seen before, you can see that this is rightly skewed. You can see the box plot, we have a lot of outliers towards the top in the higher range of value. So you can see the same thing here. As the number increases, the yield increases, you can see we have outliers, that is, that are far away from the normal range of numbers. And we can see the same thing in the pesticide tons. We can see the same thing in the average temperature. So if you look at the average temperature, you can see this right here. So for it, it is skewed to the left. That is, you have the outliers in the left range, that is in the lower value. So that is it. But this is just not enough because we have multiple crop types. So we want to plot the box plot by the crop type. So all we just need to change is the same code, but here we are specifying the crop type as the x-axis. So you can see, and our crop type is under the item column. So we just pass x-axis into it. That's all. So we have the item as the x-axis. So when we do that, it's going to give us the box plot for per crop, not just per column. It's going to give us per crop in each column. So we'll run that and we'll just wait. So you can see for yield, you can see for the different crops, we can see we have a lot of outliers. We have a lot of outliers, and that is interesting to see. And here I can see cassava, we don't have outliers. Also yam, we don't have outliers when it comes to the yield. But for the average rainfall that the crop received when the crops were planted in the areas where they were planted, you can see that for yams here, we could see the average rainfall in that area. We could see some outliers right there. And for pesticides applied, we could see a lot of outliers. That is, we have a lot of moments, a lot of times when the pesticide that was applied didn't follow exactly the same distribution across all the crops, and the average temperature also didn't necessarily follow the same distribution across the crops. So this shows variation in the data set, that there's a lot of variation in the data set. As we could see, the pesticide applied, there's a lot of variation. The temperature of the area, the rainfall of the area, there's a lot of variation. And it just says a lot about crop management or crop modeling generally. We can see there's a lot of difference in how crops perform in different regions, in different countries, in different climate zone, different climatic conditions. So that is something interesting to see here. For the skewness analysis, because we want to see specific number, we want to see how do we even know in terms of metrics if it is skewed, or maybe moderately skewed, extremely skewed, or fairly skewed. So that is what we want to do next. And the way to do that is just to use this skew method. So we just the df column dot skewed. So we are looping through the column. So we say for column in num columns, we have the num columns here already. So we don't want to repeat that. So we have the num columns. So the num columns is now, it's like a list now. And the number of columns, we can loop through it as a list, and then have the columns plotted, the columns printed out with their skewness. So here, what this code is doing is, I think is better. Let me start from the end. So what it's just doing is that if it is less, if the skewness value is less than 0.5, it is fairly symmetric. If the skewness value is greater than 0.5 and less than 1, it is moderately skewed. Then if it is greater than 1, it is highly skewed. So that is what this code is doing. So it is just direct Python. I've explained this when I was teaching for loops in the other video. So it should show somewhere on the screen. I also attached to this video, so you can watch that and really see how loops work. So I'll print this and you can see. So for the yield, it is 1.76, so it is very, very far from 1, so it is highly skewed. For average rainfall per year, it is 0.3, it is less than 1, but greater than 0.5, it is moderately skewed. For pesticide tons, it is 3.39. It is highly skewed. And for average temperature, it is minus 0.81. So it is moderately skewed because it is less than 0.5. But one of the things I want you to see that we did here is that 0.1 normally is less than 0.5. So it could have shown fairly skewed, but that is not how we measure skewness. For the skewness, if it is 0.81, it would have been moderately skewed. Then if it is minus 0.81, it will also be moderately skewed. So that is what we use this absolute value for. That is, we are saying for this for loop, ensure that you are not considering whether it is minus or plus. So it compresses everything into positive numbers, so it removes the minus. Now, we use the absolute value to plot this number, because if we don't have absolute passed into it, it could have said minus 0.81 is fairly skewed, and that would be wrong. So please look at that clearly if you want to do the same thing. So we move on to the categorical variable analysis. And for the categorical variable analysis, we want to see the crop distribution. And for the crop distribution, we want to just see the number of records that we have for each of the crop and plot that and see. So we have a bar plot. We just say data.plot. This is the most important component of the code. So we have data.plot and we are plotting the bar plot. And we have our colors. So we're just generating the colors here. And when I plot it, you can see that we have our number of records per crop, seeing that potato has the highest number of records, followed by maize and rice up to other crops. So we want to see the top 15 countries by record count. So we want to see the distribution. So here you can see top 15 countries by record count, and we want to plot it. So let's run that just the same way. And we can see top 15 countries by record count. We can see India, Brazil, Mexico. So India has the highest number of records, then followed by Brazil. And Dominican Republic is like the 15th in terms of the top 15 countries. The next thing is the average yield per crop. So it is very important to also see that, to see the different yields for each crop. So sometimes it may not be something that is directly compared in reality, because the maximum yield of potato that you can have per hectare will be different from the maximum yield of maize that you could have per hectare, because either the kilogram or the measure that you are using for them, they won't be balanced, because one could yield more fruit than the others. Not because one is better than the other, but they are different crop, they are different phenology. So we're just going to be seeing that. And just to help understand this code clearly, there's something I want you to note, which is important. Everything is the same, but something is different. You can see this norm. So what I'm doing with this norm is normalizing the data, that is the values of the yield. And I'm normalizing it because I want to use it in the colors. I want the color to show from, that is, it should show from light color to dark color as the data increases. So the higher the data, the darker the color. The higher the value, the darker the color. And that is what I have here. So when I normalize it, you can see df.group by yield, then I normalize the data that we have. So after normalizing it, then we'll pass into these colors and say plt.cm.greens. That helped me to be able to plot it this way. So if you look at it clearly, you will surely understand it. And I will advise you also practice and go through the code line by line. So yeah, that is that. So the next thing we want to see the statistics per crop. So for the statistics per crop, we want to group them together. So here you can see the crop stats, the crop statistics. We're aggregating them. So for the crop and the yield, then we aggregate it to find the mean, the median, the standard deviation, the mean, the max, and we are rounding it to 0. And I'll run that so that we can see. And you can see that now, that for potato, you can see the mean, the median, the minimum of the potato. And you can see for soybean, you can see the minimum is 50. And for the mean value is 165. And the maximum is 41,609. So this is something good to see. So if you're analyzing this and you have to present it, it is always good to see these variations of the yield of different crops, yield of also yield in different areas. Those things are very important to see. So this is the univariate analysis, and for the bivariate analysis, we are going to be comparing two variables together and see their association. So see if they are correlated or not correlated. So I'll move to the bivariate analysis now. So you can see the bivariate analysis, and the first thing is we want to do correlation. So, and the first correlation we're going to be doing the correlation of all the numeric columns. So we're using sns.heatmap. So this is the main component of the code, and every other thing is just, this one is for the plot, and this is to set the title and the plot the layout. So you can see we select the data type first, just the numeric, then dot correlation, that is .corr is the method we are using from Seaborn. Then we annotate. Annotate means add the values of the correlation value on the plot. That's what annotate is doing, and have it in 2 decimal places. That is what this .2f is doing, and every other thing is just the decoration of the plot. So when I run this, you can see for the year, of course, when you see 1, 1, 1, 1, 1, of course, it is the same variable. There will be 1 when you correlate them with each other year by year. But here you can see that it is difficult to really see a strong pattern. Apart from, you can see there's a correlation between average rainfall and average temperature, even though the correlation is not very, very high, but it is something good to see. So 0.32 here. Then for pesticides and year, you can see 0.15. But that is the comparison. That is the univariate analysis. So depending on the goal of your analysis in the end, this can let you understand things. So for example, for machine learning, when we have 2 variables that are highly correlated, sometimes it is better to drop one of the variables because they won't be telling us anything new if they are highly correlated. So it is usually sometimes just better to drop the column sometimes. So depending on the goal of the analysis. So let's do a pair plot and just see something clearly. So for the pair plot, it's going to be showing us like a scatter plot and also showing the interaction between 2 different variables. So the pair plot sometimes takes longer time. Let me see how long it takes here. So the pair plot helps us to see the interaction between the 2 variables. Just like we were able to see correlation here, we can be able to then see if the interaction between 2 variables, if it follows a specific trend. So this is the pair plot, and you can see for the pair plot. So the pair plot helps us to see also the distribution of the column itself, then also the trend, the interaction between 2 columns. So we can see here the yield, and let me see the pesticide ton. So we can see here the yield and the pesticide ton, per tons rather. So we can see that over here. So it helps us to see the interaction between the 2 variables. So, and if there's a strong pattern, we would have seen that directly. And here we are coloring it by the crops. So, and it is normal, it's not surprising that we see the maize and the potatoes dominating in terms of the color, because we have maize and potatoes. They are very high in the number of records that we have. But that is something interesting to see. The next thing to see is the top 5 country crop combination by their yield. So let's look at that. So here you can see we group them by area and item, and we want to use the yield. Then we do the aggregation and say .mean. And what .frame is doing is show us like it is a Pandas data frame. Then we sort the value by the yield, and ascending is false. So that is, go from high to low. If ascending is true, then we go from low to high. So let's plot the top 10, or we can just remove 10 and just plot the 5. So you can see that. So United Kingdom, and potatoes in United Kingdom happens to be the highest in terms of yield, followed by France, followed by Germany, followed by Australia, and followed by Japan. And yeah, that is it. Well, it is not surprising to see that it is that way. So we move to the next thing, which is the rainfall and pesticide use per country. Rainfall and pesticide use per country. So let's see that. So for us to see this, the first thing that we need to do is, for the plot to be easily comprehended, we'll divide the plots into different categories so that we don't have like 71 bars. Let's say we are doing a bar plot. So we want to have like maybe 7 plots or 8 plots with about 10 bars on them so we can easily see them. So that's why we have areas per plot. We say 10. That is the number of countries that we want to have in each of the plots. We say 10 countries per plot. Then the unique areas, I want to get the unique areas from the data. So that's why we say df area.unique. This will pull the unique areas, then we sort it. So when we sort it, we want to go from, in this case, ascending is true by default. So we are going from A to Z, not Z to A. Then the number of plots, we are using this mat.cl. Then we say the unique area divided by the areas per plot. So this will help to know the number of plots. So mat.cl will help us to know the number of plots. That is, I should have 8 plots. That's if I divide, let's say 71 by 10, that would be 7.1, right? So that means that will give me 8 plots in a way. In this case, because it's supposed to be 7 plots or 70, but the one is going to have 1 plot with just now 1 country. Then we now divide the area into chunk. So that's what we are doing. We say the unique area, and we go from the first to number 10. Then we now say for I in range 0 to the length of the unique areas. So the length of the unique areas that we have, then we have the areas per plot. So that is what this is doing. So when I run this, and let's say I print area chunks to see what is in it. So do you see the area chunks? You can see in each of the chunk, we have Algeria, Angola, Argentina in the first chunk. Then the next chunk, Cameroon, Canada. So we have 10, 10 in each of the chunk. And we'll see why that is useful now. So when we make this plot that we want to do now, so here we are having this plot of average rainfall per country group. So to see it clearly, so the main thing that I want to see here is as for I in range mean 8, then len of area chunks. That is, go to the areas that we have and pick each of the chunk and you make that plot for them. And the plot we are making here, you can see we are grouping by area, and we want to see the average rainfall per year for each of that area. I already explained what we do with normalize the other time. It is for us to be able to plot the colors so that the higher the value, the darker the color. So that is what we are doing here. So it is just basically the same thing that we've done before, just that in this case, we are plotting by area. So it will go chunk by chunk. So if the area is in the first chunk, we have the first plot, the next chunk, we have another plot, and that continues until the last one. And here we're just hiding on use of plot in case there's a plot that we're not going to be using. So when I run this, you see that. So you see, so normally this would have been, let's say 70 bars and a big plot, which would be difficult to read. So that's why we group the countries together 10, 10 so that we can have it clear. So here you can see the last country is Zimbabwe, and that is why there's a specific plot for Zimbabwe. So there's another method where you can plot Zimbabwe with other plots, but in this case, just for clarity, we have it this way. And we can see the average rainfall. We can easily see where we have the higher rainfall in terms of the color and the length of data. In Bangladesh, the average rainfall is very high. In Colombia, in Indonesia, in Guyana, in Mauritius, Nicaragua, Papua New Guinea, then in Suriname. So, and if we want to do like a geospatial analysis to really see what is common between these countries that make them have high average rainfall, that is something we can also explore further, and we can get a lot of things there. So we'll move on to the next analysis, which is the pesticide use per country. So just like the way we did the rainfall, is just what just changes here is we just add the pesticide. It's the same code, then we just add the pesticide tons instead of the rainfall that we have. Now we just have that and we plot, and we just change the metadata, the description. So, but the main thing changing in the code is the variable name or the column name. So I'll plot that for us to see. So you can see in terms of the pesticide use, we can see that in Brazil, they use a lot of pesticide. In group 1, in Colombia, a lot. Canada, wow. Italy, Japan, France, Mexico, Spain, and Ukraine. Now, looking at this is trying to tell us something. Is if France has a lot of high yield of potato and they use a lot of pesticide, does that mean pesticide has an effect on the yield? Is there an interaction between pesticide and crop yield, or is there an interaction between rainfall and crop yield? So we can't directly answer that by just looking at this. We need to do that comparison. We need to correlate them to see maybe the higher the rainfall, the higher the yield, or the lower the rainfall, the higher the yield. Is there an opposite interaction or interaction going in the same direction? So that is what will lead us to the next thing here. So you can see pesticide and rainfall effect on crop yield. So we're going to be doing the correlation. And what we are doing in the correlation here is we want to correlate the pesticide and crop yield together. So the first thing is you need to drop the NA, that is the if there's a null value or a missing value, and that is what this line of code is doing. I'm going to be plotting that so that we can see. So we do the pesticide versus crop yield correlation. Okay, let me show this easily. Then we also do the rainfall versus crop yield correlation. I want to visualize them side by side, and that is what I want to see here. So the first thing is for the correlation, we have the pesticide correlation. So for each of the crops, so we're doing it per crop. I want to correlate it per crop. Okay, to do this correlation, what we do here is number one, we need to capture all the crops, all the unique crops into this list. Then this line of code, what it is doing is it's a dictionary. And for this dictionary, we'll be appending things to it that we're going to be using for the plot later to sort the value. So we say for cropping crops, that is for crop, that is each of the value that we have in the crop list, filter that specific crop by saying df item equals that specific crop, then we want the pesticide tons column, then we want the yield column, then we want to drop the missing value. So because we cannot do correlation for data point when it is less than 2 rows, for a data frame when it's less than 2 rows, so here we need to set the condition that if the length of the data frame is greater than 2, then do the correlation. If it is not, there will be no correlation. So then we have this dictionary, and the dictionary, we have our crop here. So the crop name will be the key. Then the correlation value will be the value in this case. So dictionaries, we have key value here. There's a video on dictionaries on this channel. Please watch it if you don't understand dictionary. And here we convert to a Pandas series and we sort the value. So we repeat the same thing for rainfall. So the only thing changing here is just the average rainfall, and here we have the pesticide in tons. So to do the plot, the main thing in the plot, every other thing is like decoration, but the main thing is this plot. So we make it as a bar plot and we plot it. And the axis 0 and axis 1, what we are just doing is we are trying to ensure that we have them side by side, like I've written in the comment section here, that is visualize them side by side. So when I run this, you see, now we have the correlation plot. Now look at this correlation plot. For soybean, there's high correlation when it comes to pesticide use. So compared to yield, with yield, pesticide versus yield correlation. So here, is this safe to conclude that for soybean, using more pesticide increases crop yield? Is there that interaction there? So maybe we can't be very quick to conclude such, but it is something good to dig deeper into, because sometimes correlation is not causation. So we might have seen that pesticide has a meaningful correlation with the crop yield for soybean, for example, but it's not necessary that the pesticide is the reason, it's not a cause. So in causal analysis, you can do that further. But here, it is just a good pattern to see. Now we can see that for plantains and other crops, or for yam, there's a negative correlation, even though it is not a lot of negative correlation. So there's really no good pattern here, but it is always good to dig deeper into soybean and potato, at least, because they have a bit high. We have around 0.3 in correlation. Now for rainfall, there's really no much. I'm surprised because I expected that there will be a lot of like high correlation, or higher than this, when it comes to interaction between rainfall and crop yield for each of the crop. And here it is surprising to see that there's a negative one. That is when there's high rainfall, the crops don't perform very well. So there's an opposite correlation. So that is strange for me to see anyways. But through causal analysis, you can dig deeper into whatever we're seeing on this plot. Then the next thing we need to see here is the time series and trend analysis. It is good to look at that. So we want to see the average yield over time. That is the first thing here. And the main thing you need to see in this code is this axis of plot. So yield by year, then the yield by year dot value, then we have the marker. All these are mainly like decoration for the plot. So later we're going to have a video on Matplotlib and Seaborn and how to make like beautiful plots with them. But in this case, I want you to just focus on the ax.plot, and we capture the index and we want to plot the year values and just see the trend. So let's plot that so you can see this. And from 1990, there's been like meaningful growth, at least over the old data point, that is in all the country. So we can see here in terms of the average, so you can see 80,000 on the yield here, the main yield. So if you go, started increasing up to this year, which is something good. It's a good pattern to see. But can we see the same trend per crop? It would be a good thing to see. So let's see the trend per crop. So just like what we've done before, for everything, we want to see the trend per crop. So we're just going to loop through each of the crop and have the plot of their trend. So you can see that for, I think it's cassava, there's like a drop around here. But for others, it's a bit stable. But I think for potatoes, there's been a lot of high yield. So this is something good to see, because here, when I do it for everything, it looks like, oh, there's so much increase because we're going from 60,000 to 80,000. If we look deeper to it, we see that for some crops, there's really no increase in the trend over the years. It's basically the same when it comes to the crop yield. But that is why it is good to dig deeper into these things. So pesticide usage trend over time, we want to see, this is the yield trend. Then we want to see the pesticide usage. So for the pesticide usage, I'll just plot it. And we can see the pesticide usage. See? So generally, there's been an increase in the use of pesticide. But if we do it per crop, we're also going to see the different ones. So this has been a good analysis so far. But the last thing that we need to see here in terms of the analysis itself or the plot that we are making is to visualize it geographically. So that is where the geographic visualization comes in. So I'll do this, and we'll do what we call the choropleth map to see the average yield per country, to see it in a map. So I think that is easy to understand compared to other ones. And this is what the choropleth map comes in. We are getting it from the Plotly lab. That's why we have the PX, and we print the location, which is the area. In this case, the country name, the yield, which is going to be what we color based on. The color is the greens, then the average crop yield per country, and the labels is going to be the yield. We call it the average yield. And for this, we don't necessarily need to normalize the color. For the map, it will normalize the color itself for us. So I'll just run it to plot the map, and we can see our yield. So you can see that, wow, United Kingdom, just like what we said before, you can see the average yield. We have high yield there. Let me see if we have other places with interesting. In Germany, also a bit high, but we can see in South Africa it is low. In Angola it is low, and all these parts we don't have any data point in. I think this is Russia or somewhere here, and in the United States we don't have any data point in our data set. So this is something interesting to see. You can see the average yield country by country, and you can easily see directly that United Kingdom, there's high yield here. And this is a paper standard plot that you can make, and you can improve on it and export it. So let's see the average pesticide used per country, and just the same plot for the choropleth plot, and you can see average pesticide used per country. Here we can see in Brazil there's a lot of pesticide consumption, pesticides used, but when we look at their yield, you can see that they don't have as high as they do in the United Kingdom, and the United Kingdom doesn't use the same amount of pesticide as they do. So you can see here 28,000 usage, and here you can see the average pesticide is 199,000. So that also tells us something, that the pesticide application may not necessarily be the reason for the crop yield. So for the average rainfall by country, it is also good to see that on the map. And you see this in Canada, you can see the rainfall is high, but from the whole data set, you can see in Colombia there's high rainfall. In Papua New Guinea there's high rainfall. Indonesia, and yeah, other parts, Thailand, Bangladesh, and this is just something beautiful to see. So basically, these are the things we do in exploratory data analysis. And one thing I want you to know is that the analysis will always, there's a goal of the analysis, and that goal will guide the specific analysis that you do. If another data analyst or a data scientist picks this data set, depending on the question they want to answer, there's a way they will manipulate the data to give them specific result that will help them understand and meet the goal that they've set for the analysis. So finally, let's just look at a summary. So the summary that has been written here before. So we can see here that the dataset contains crop yield data across multiple countries. Then we have the 10 different crop types in the data. Then the variables include the yield, the rainfall, pesticide usage, and average temperature. Then the data was checked for missing value, and the heat map shows completeness. So we have no missing value. Then the yield and pesticide usage are heavily right skewed. So which means we have a few countries where we have more crops, and the boxplot reveal significant outliers across the data set. And for the correlation, we can see that pesticide and rainfall correlations with yield vary greatly. And I've said that before, we can see the different variation, and some crops show positive correlation with pesticides, more pesticide, high yield in some cases, and while others show negative or no correlation. So rainfall alone is not a strong linear predictor of yield across all crops. And this is a good thing to know, because when we do the machine learning part or project to predict crop yield, knowing this helps you understand your data better and to be able to build a better model. And for the trend, we can see yield have generally improved over the years across most crops, and pesticide usage trends show patterns that may correlate with policy changes. So as policy changes, the pesticide usage will change. So in this case, let's assume we have fertilizer application. In this data set, we see how that also changed over the years. So because there may be policy that could be, oh, you are not allowed to use more than 200 kg of fertilizer, or not allowed to use more than 200 kg of pesticides. And we can see the geographical pattern that there are clear geographic clusters in yield, rainfall, and pesticides. So we can see them that in some parts we have high yield, in some parts we have high rainfall. That could have a relationship with how developed the country is, how good the policies are, or the kind of farming operations that they carry out in those countries. So you can see the higher countries, they tend to be in the temperate region with moderate rainfall. Although rainfall is not the only predictor, but we can see that if they have completely low rainfall, they can't really have high yield. So rainfall is a contributor, but not the only predictor, because it does not have a complete direct linear relationship with crop yield. So the key takeaway here is that the relationship between inputs, for example, the pesticides and the rainfall, and the crop yield is crop specific. So here we have a non-linear interaction. And that says something when we are building the model. So this tells us now that the model that we are going to be using that will perform well for this kind of data set, it has to be a model that can model complex relationship, that is non-linear relationship. And if we even have a reason to do feature engineering in the machine learning phase, we need to engineer our feature to be able to work well with models that can model non-linear relationship. So, and simple correlation, just like what I was saying about non-linearity, the simple correlation cannot capture the full picture. So you can see the crop type, the country, and the time, that is the specific year. They are all important factors, because crop yield is not just necessarily about how good farmers are practicing on their fields. It's also dependent on policy, market access, sometimes global economic issues. All these affect farming operations at large. And I hope this analysis has shown you something, and I want you to try it yourself and let me know in the comment section if you have questions, or you may even have disagreements with what we've analyzed, and I'll be really interested to know what you have in mind, so that we can have better tutorials for people to learn data analysis and machine learning as they go in their data science journey. So thank you very much, and this will be where we end this tutorial for now. Like this video and subscribe if you are yet to do so, so that other people can benefit from this video.